so let's first look at what we did last week at the very end. This one will help us to understand the first topic of today's class. We apply n qubit Hadamard gates on n qubit system, and of course, when we say n qubit Hadamard gates, it need to be applied to n qubit system, right? You don't do an operation that does not belong to the space. 1 qubit needs to be 1 qubit operation. What's the size of the matrix of a 1 qubit system? 2 by 2. Anyone can explain why he said 2 by 2 for a 1 qubit system? Why the operator is 2 by 2? Okay, 1 qubit is 2 by 1, but why 2 by 1 for 1 qubit? That's not what you said also. 2 basis states, right? 1 qubit, you have 2 basis states, right? So your matrix need to be 2 by 2. How about 2 qubit? How many basis states do we have? 4. Make sense? 0, 0, 0, 1, 1, 0, 1, 1. So what is the size of the operator? 4 by 4, right? And how about 10 qubit? Others? What is the size of the operator? Okay. When I say others, it doesn't include you. Otherwise, both of you just just kidding, right? That's not a swap game. Anyway, yeah, 2 to the power 10, right? So, I mean, these are the basic things, right? If you still get confused, please ask me now if you have questions. Okay, so we applied n qubits. So what is the size of the matrix? What's the size of the matrix for n qubit? 2 to the power n times 2 to the power n, right? And we applied this to n qubit, and we assume it is at state 0. Okay, all of them are 0. So we went through some math. This math is easy but confusing. First of all, you need to recognize that when I say I have Hadamard gate n qubit, I can just say that it is a tensor product of n 1 qubit Hadamard gate, n 2 by 2 matrix, right? Tensor product. Apply to n 1 qubit at its ground state. That's why we have tensor product n, right? Is this clear? Or you ask yourself, if I put this in exam, do you understand what I'm asking? If no, you should ask now. So I expand it, this become H, tensor product H, tensor product H. I add 0, 1, 2, 3 to n minus 1 just to label. I don't need to label them if you agree with each other. Otherwise, I label it just to show that they are at different space, right? Or they belong to different electron if it is a spin qubit. So first electron, second electron, nth electron. But I label it from 0 to n minus 1. And same, this operator applied to this basis state 0, 0, 0, 0, 1, all the way to n minus 1. So this operator can apply to which qubit state, which cat state can receive hn minus 1. 0, n minus 1, right? Although you won't make mistake even you do that, but physically this is applied to this because we're talking about this space. This belongs to the nth electron, nth minus 1 electron. Then you need to be the operator belong to that. For example, it means the laser pulse I shoot on the nth electron, or the microwave pulse I shoot on the nth electron. You cannot say that the laser pulse applied to the first electron, affecting the nth electron. It may, but then it becomes a bigger system. But assume they are isolated. I don't care whatever you do to yourself. It should have nothing to do with me as long as we don't have interaction, right? Make sense? So if this is the case, I can easily just, okay, I just care about each space. So I apply H to this 0, this H to this 0. So that's why it is the same as applying H to each 0 and then do the tensor product. Right? And then you might want to recall, okay, if I have matrix form, how do I do this? This is something we may appear in the exam, right? And then we remember when H applied to 0, what's the result? It becomes a superposition, right? And this is a review already. I mean, we mentioned this many times, right? You define a quantum gate by defining how it transforms the basis state. And for Hadamard Gate, it transformed the 0 to 0 plus 1 over square root 2. You should memorize this, right? Of course, you have cheat sheet. Then, same for others. And then you just do tensor product. And this, how do you do tensor products? For scalar number, I just group them together. So 1 over 2 to the power n over 2. And then the rest, I just do permutation. Just do whatever you do when you are doing the binomial expression, a plus b to the power n. Although now it's tensor product, we did not prove anything rigorous, but you just trust me, it follows this rule. So that's why I have 0 times 0 times 0 all the way to times 0. This gives me 1 cat, right? And then I have 0 times 0 all the way to 1. Then this is another cat is 0, 0, 0, 1. And if you think about that, there will be 2 to the power n permutation, right? Because n times 2 times 2 times 2 times 2. I mean, 2 times 2 times 2, right? So that's why you have from 0, 0, 0 all the way to 1, 1, 1, 1. And then we recognize this. If you learn from the digital logic, binary logic, you know that if you have an n register, the value can go from 0 to all the way to 2 to the power n minus 1, right? Here I have one step. I just group them together. There's nothing special. And then this is in binary number. Now I write it in decimal number. And so it is a summation from 0 to the 2 power n minus 1. So, and I write this summation here. Any questions? Is this clear? Yeah. If you need to use this equation, you can just use it, yeah. Oh, okay. The good thing about my exam is I don't test difficult proof. So don't worry that I'm doing some like math class style. No. What I want is application, okay? But you need to understand what I'm proving, because these are the basic concept. Then you might need to use those concepts. But I do want you to understand, okay? You don't need to memorize how to prove it. That is not useful for this class. Make sense? Okay. Now, the reason I spend time on that is because now I want to ask another question. What happened if instead of applying, right, Hn to 0, I want to apply it to a general state Y? The difficulty of this one, actually, the first thing is, do you understand what is the meaning of this question? Can someone explain to me what is the meaning of Hn applied to a state Y? What's the meaning of Y? Yeah. Excellent. He said that Y is now a general case, it's a combination of 0 and 1. So first of all, how many qubits do we have in Y? Should be n, right? Because we're talking n qubit. So that's why, as like what he said, I'm going to write it as H, right, n. To make this very clear, what is the meaning of Y? Y is Y n minus 1, Y n minus 2. All the way to Y n minus, Y 3, Y 2, Y 1. So, no, and then Y 0. So I have n digit, right? Again, some of you may say, why I have n minus 1, but I start with 0. That's why it's n digit, right? And it's in binary. The easiest thing to understand this is, let's look at an example. For example, n equal to 4. And then y equals to 9. This is a decimal number. Okay, so how do I write y in binary form? It is equal to 1001. Is that okay? And everyone remember the binary representation? If not, we remember that 9 equals to 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0. Do you see this? That is the meaning of the binary representation, right? Just like when I say 99 in decimal, it means 9 times 10 to the power 2. 9 times 10 to the power 1 plus 9 times 10 to the power 0. That's called decimal system. The base is 10. Now it's binary. The base is 2, right? So I write it at 1001 because this represents 1 part of 2 to the power 0. This represents 0 part of 2 to the power 1, 0 part of 2 to the power 2, and 1 part of 2 to the power 3. That's why you add together equal to 9. And that is the binary representation, right? So for this state, it can go from 0 to 2 to the power n minus 1. Okay, let me ask you, when n equal to 4, what are the possible values? I just gave you the equation. Any other people, not just those who have answered? What are the possible number when n equal to 4, when I have 4 bits? Say again, 16 possible values. What are those values? You say 16, right? But what are they? 0 to 15. Yeah. Make sense? And 0 is, in binary, is what? No, binary. I mean, for 4 qubits, say everything. 0, 0, 0, 0. Okay. How about 15 for 4 bits?
4, 1.
1, 1, 1, 1. I know it's simple for some of you, but you cannot get confused when you're doing quantum computing, right? This basic thing. Any questions? And basically, this is the question. I apply it to an arbitrary state. Okay, if n equal to 4, y can be 1001, 1111, 0000. Now the question is, what's the result? Our goal is to come up with a general equation, and that is one of the assignment problem, right? I asked you to do substitution. Okay, so maybe here I actually want to say this also. Just recall. If you forgot, y equals to summation I equal to 0 to n minus 1 yi times 2 to the power I, right? That is the how you really calculate the value of a binary representation. That is exactly what I'm doing here. Okay. The easier way to learn is to plug in numbers. Okay. Okay, great. So based on this equals to what? I will decide to, again, like what we did for the 0 case, apply it to each qubit. Okay, so this is equal to h, apply to yn minus 1 for the dead space, tensor product h, yn minus 2, tensor product h, y0. We need to pause here. If anyone don't feel comfortable with this, please raise your hand. Or if you have question, you should not get confused by this anymore. You need to know this, right? Any questions? Is this clear? What we are doing? Why I can go from here to here? The operator, yeah, it is n qubit space 2 to the power n, complex number space. So I have n h tensor product together. But each of these h apply to each of the qubit. And that's why I can write this. And I hope you are okay to recognize that this whole thing is the tensor product of n qubit. I write it this way, is the same as ket yn minus 1, tensor product ket yn minus 2, all the way to tensor product ket y 0. Right? And y I can take 0 or 1. Questions? We are reviewing. If you don't know this, you may fail the class, the exam. That may give you more incentive to ask questions. Okay? Okay, so let's continue, right? So now I will study, okay? Instead of studying the whole thing, it appeared to me that I should study a general term. I'm going to consider h applied to yi. So this I can be any I, right? And yi can be, what are the possible value of yi again? Numerical value, what are the possible value? 0 and 1. Oh, I know it's trivial, right? But I want to make sure that you are on track. So if I apply to yi, what can be the output based on the behavior of the Hadamard gate? That's why it's easy for quantum computing for 1 qubit. What can be the output? Plus or minus. So, okay, when would you get plus 1 over square root 2? This is plus, right? 0 plus 1. So this is review, okay? When would you get this one? When yi equal to? Thank you. And then what do you get if iy is not 0? Minus, right? It can be only either 0 or 1. Is that okay? Now I want to combine them together. This is nothing but just, you can guess, but I give you the answer and then you can check. This is 0 plus 1 plus negative 1 to the power yi. 1. Let's check if this is the case. When yi is 0, what is negative 1 to the power 0? 1, right? Anything to the power 0 except 0 to the power 0 is 1, right? So it is 0 plus 1, right? When yi is 0, correct. When yi is 1, what is the negative 1 to the power 1? Negative 1, right? So this is 0 minus 1. So I have written an equation without using the condition, right? It's just like in programming, instead of if then else, now I just give you the equation directly. So h applied to yi is this. And of course, the assumption is that yi needs to be either 0 or 1. And that is the case. We only have 0 and 1. And that is the beauty of the simplicity in quantum computing when it is 1 qubit. Very often, we just need to consider 0 and 1. We come up with something very elegant. So when you read papers, sometimes they will give you this. Don't panic. You will feel that, how come this is equal to this? Then think about, oh, there are only two conditions, 0 or 1. Let me substitute. Very often, they will have this type of equation. Okay? So good. So I know what is HYI. So if that is the case, I do have plenty of space. Then I consider everything, okay? And apply to y. Of course, then it's going to be equal to 2 to the power n over 2 because I have many 1 over square root 2, right? And then for each term, what is this? It's 0 plus negative 1 y to the power n minus 1, right? Because this term is I equal to this is I equal to what? This term. I equal to what? Right? We are using this equation. Right? I apply h to yi, it gives me this. So I apply h to y n minus 1. Right? So I equal to n minus 1. Is that okay? Right? I'm talking about this. Right? I'm applying h to each of this term. So the first term, h applied to yn minus 1, based on this, is this term to the power yn minus 1. That's why I have this. Make sense? Then I continue the rest. Of course, it's tensor product 0 plus negative 1 yn minus 2. Right? And then continue. The last one is 0 plus negative 1 y0. 1. That gives me everything. Is this okay? Right? What can we do now? Now, so we will do some trick so we can see the structure better. So I'm going to write this as 1 over 2 to the power n over 2. I'm going to put negative 1 to the power 0 in front of the 0. What is negative 1 to the power 0? 1, right? So when I put this in front of 0, I don't change anything. But I just put it here because I want to show something later. Okay? So I just put negative 1 to the power 0 in front of it, and then the rest are the same. Right, I just put negative 1 to the power 0 in front of 0 cat because it does not affect anything. Negative 1 to the power 0, 0 plus negative 1 y0, 1, right? Okay. Now, if we recall what we did for the 0 case, this is the same. I have many 0 and many 1. Again, if I multiply them out, I will get 0, 0, 0, 0, all the 1, 1, all the way to 1, 1, 1, 1, 1, right? So, but I'm going to write them in the decimal form. Then I will get this. I will get the first one, of course, is 0. Everything is 0. I'm writing it in decimal, right? And then what are the coefficients for the decimal? It's just negative 1 to the power 0 all the way to negative 1 to the power 0. I have n of them, right? Because this 0 times this 0 times this 0. Make sense? Again, this is a decimal, right? So I have n0 here. This one means I have 0, 0 all the way to 0 in binary. If you don't see it, maybe I do the last one first. Right? The last one, maybe it is 2 to the power n minus 1. What are the coefficients that give me 2 to the power n minus 1? So 2 to the power n minus 1 is decimal. What is the form in binary? What is that? It's all 1, right? It's like we start getting lost. 2 to the power n minus 1 is all 1. Right? How do you get all 1? This term times this term times this term. Right? So you will get it by negative 1 yn minus 1, negative 1 yn minus 2, all the way to negative 1 y0. Right? Is that okay? Okay, then I just fill in other term for 1. 1 is like 0, 0, 0, 0, 0, 1, right? Everyone is falling there. Okay, you tell me. What is 1 in binary? 0 in front and then 1. How do you get n minus 1, 0, and then 1? From here, from this multiplication.
N minus 1 zeros.
There are n minus 1 counts of 0, and then 1 at the end. Which one multiplied will give you this? This one. You need to have like 0 times 0, right?
Yeah, you have all the zeros.
Exactly. All the 0 except the last one, right? And then what is the coefficient of all the 0? Negative 1 to the power 0, negative 1 to the power 0, right?
Yeah.
And then eventually negative 1 to the power 1, 0, right? I try to trace this. But then eventually negative 1 to the power 0, okay? Doing this is maybe not very useful, but what I want to tell you is that after this expansion, I get a coefficient. I call this C0. This is C1. This is Cn minus 1. The point is that even this is arbitrary, I still get something like this, 2 to the power n over 2. And then C0, 0, plus C1, 1, plus C2, 2, plus all the way to Cn minus 1, not Cn minus 1, should be C2 to the power n minus 1, 2 to the power n minus 1. Make sense? I still have all these bases kept, but I have different coefficient. Of course, it is still 2 to the power n over 2, summation x equal to 0 to 2 to the power n minus 1. But then I have Cx, x. I just want to show you that everything is the same as what we did earlier, except that the coefficient is more complicated. Right? Let's compare to this again. This is the coefficient is 1 in front of all of them. Okay, I call it x. Let me call it, I need to call it x because of the textbook, but I call it k earlier, right? But it doesn't matter. I can call this x also. This is the same as 2 to the power n divided by 2, x equal to 0, 2 to the power n minus 1x, right? Do you see that? Right? I just sum over the x. And here I also sum over the x, but each of them has cx in front of it. Now the question is, what are the possible value of cx? Who say that? He said, why do you think, why you're so confident is this plus minus 1? Thank you. Exactly, because what I've shown you before is just 1 times either negative 1 or 1. You just have all this combination, right? So clearly, Cx must be equals to plus minus 1. Okay, so our goal is to find Cx. Okay, is that okay? Now, so if you ask, of course, you don't need to memorize how to prove it, right? It's meaningless to memorize how to prove it. But here we have gone through a lot of important concepts, including tensor products, how to convert binary to decimal, how to have a compact formula, and most importantly, you recognize that applying Hadamard Gate to any basis state, you get a superposition of all the basis states, except the coefficient is plus minus 1. Right? And then the next step is to find out what is Cx. So what is Cx? So let's let me see what I'm trying to do, right? So let's consider a general term. Right? And this term is x, right? I'm trying to consider x. So I have xn minus 1, general term with x, right, equals to xn minus 1, xn minus 2, all the way to x1, x2. Again, it's n qubit, right? This x is the basis state. So again, it has n qubits. So now I call it x1 to xn, xn minus 1 to x0. Make sense? Okay. So we consider this term, right? We have what? So we have maybe I should call it, let me just, Cx, I call it Cx equals to, if you look at Cx, what does it have? It actually has negative 1 to the power xn minus 1, yn minus 1. Negative 1, xn minus 2, yn minus 2, and then all the way to negative 1 x0 y0. So why is that? Because when you have x equal to 0, yeah.
Is that a sum or is that a product?
These two?
Yeah, all the whole term that we see that.
It's product.
Okay, so you have a plus that.
Negative 1 to the power of this times negative 1 to the power of this. Oh, so yeah, so there is a typo. Thank you. So that's, thank you. Yeah. Should be dot, dot, dot. The reason is this. We have this. Why? Because you get, in the term, right, we get negative 1 to the power 0 if x n minus 1 equal to 0, right? If you get, you remember this is by multiplying the coefficient in front of 0 or 1. You get a negative 1 to the power 0 as one of the term if you actually have x, the corresponding digit, equal to 0. Okay? And you get negative 1 to the power yn minus 1 if xn minus 1 equal to 1. Right? If, let's look at this term, right? If one of the digit is equal to 1, when it is 1, this 1 must come with the coefficient of negative 1 to the power n minus 1 correspond. Maybe I should say, maybe let me make it clear, right? I should say because, let me say for example, right? Because, for example, when let's say for n minus 1, for the n minus 1 case, we just take one of the case, right? The n minus 1 location, if this is equal to 0, then it means you actually get negative 1 to the power 0 during the multiplication. If this is equal to 1, then you would have get negative 1 to the power yn minus 1 during the multiplication, right? And that is what I'm trying to say. If it is 0, xn minus 1 equals 0, you get negative 1 to the power 0 during the multiplication. Otherwise, you get negative 1 to the power yn minus 1, right? And these two, again, we can combine them as equivalent to negative 1 to the power xn minus 1 yn minus 1. And it's easy to check, right? If xn minus 1 equal to 0, then for sure this is give you 1 and this is 1, right? If x1 equal to 1, then of course this is negative 1 to the power yn minus 1. Right? So these two equations is equivalent to this equation. So each coefficient is come from the multiplication of this n coefficient. That's the Cx. I know it's confusing, right? So let me repeat one more time. Let's go back one more time. How do you get the coefficient? The coefficient comes from either negative 1 to the power 0 or negative 1 to the power yi. Make sense? Because you multiply them together, right? When do you get negative 1 to the power 0? You get it if it is 0. It is a 0 bit here. Let me give a general form. X, right, equals to xn minus 1, xn minus 2, all the way to x2, x1, x0. For each of these terms, they have a binary representation. So any x can be represented as x to the power xn minus 1, not to the power, but subscript. Right? And if this n minus 1 is 0, for example, it must be a 0 from here, right? It comes with negative 1 to the power 0. If xn is actually 1, it comes with negative 1 to the power n minus 1, because that is how you construct this. Make sense? And because of this, we come up with this equation. So this C is equal to this. Okay, maybe this is, you can ask me later. Let me finish this. I think I don't explain it well, right? But after all, let's just learn how to use it. So what is this? So Cx is just equal to negative 1 to the power x dot y. This is not multiplication. This is actually an inner product or exclusive OR. So it's x dot y. It means xn minus 1 times yn minus 1, exclusive OR xn minus 2, yn minus 2, exclusive OR all the way to x0, y0. So basically, it's trying to count the number of positive, number of 1 of this x dot y. Okay, for example, this is something similar to your assignment. If x equal to 1, 0, 1, y equal to 1, 1, 1, what is x dot y? Can someone help me?
Take n minus 1 times 1.
Okay, n minus 1 times, very good. 1 times 1, and then 0 times 1, and then 1 times 1. So 1 times 1 is 1, 0 times 1 is 0, 1 times 1 is also 1. Then what is 1 exclusive or 0? What? What is 1 exclusive or 1? 0. So x dot y in this case is 0. Okay, then what is the coefficient? Then Cx equal to negative 1 to the power 0 equals to 1. Then your coefficient is plus 1. Okay, so in summary, we prove that h n applied to general y equals to 1 over 2 to the power n divided by 2 summation x equal to 0 to 2 to the power n minus 1. 0, negative 1 to the power x dot y, x. This is a review also. Do you understand this formula, right? You don't have to memorize. What is the meaning? Anyone want to explain it mathematically or just work qualitatively? What is the meaning of this formula? It means when I apply Hadamard Gate to a general basis y, what is the output? The probability is 1 over 2 to the power n. Very good for each of the bases. And what are the bases? Yes, the bases are 0 to 2 to the power n. It means every basis in the space, right? So again, it looks like an equal superposition, except that they have a phase of minus 1 to the power x dot y. And this x dot y is defined by this. Basically, it's just like a vector. If you treat x as a vector, right? Because you see this is like a vector. And you can treat y like a vector. This is also a vector. The inner product, and then modulus 2, right? You have odd number of 1, then it is negative. You have even number of 1, then it is positive. So it is going to be plus minus. It might not be alternating depending on the value of y, right? But it's either plus or minus. So the whole thing should not be difficult, except this part is a little bit confusing. But try to think about it. There's some, I don't teach you well, but something you need to keep thinking in order to understand. Okay? Any questions regarding this part? This part is very difficult to explain. If you look at the x dot y, yes. And if you have even number of I, of 1, then it's negative.
So x is not
X dot y, x is the number in the cat, y is the cat that you apply to, right? Which makes sense. Your result should depend on the initial state. Yeah. Actually, we have an example, but let's go back to that later. Or maybe we can start with that one, right? So that we will, let's just, I jump to slide 9, okay? We start with that one. So I want to find, my question is to calculate the H operation. This is a review again. You know how to do it already, but let me start with this method 3. We use the equation. I call it method 3. What equation? I want to use Hn applied to y equals to 1 over 2 to the power n over 2 summation x equals 0 2 to the power n minus 1 negative 1 to the power x dot y and then x. I want to use the equation we just derived. And the reason is we really want to understand this equation because you're going to see this very often later in quantum Fourier transform, Gauss algorithm. If you don't understand it, you don't need to know how to prove it. But if you don't understand it, you will get into a lot of trouble. So let's start with this. My question is, what is my goal? Okay, I want to set y equal to 3. What is that in binary number? 1, 1. So I also want to say this is y1, y0. So what is y1? 1. What is y0? Also 1. Can you follow? Okay. So my question is, what is n now? What is n in this case for what I've written? 2. I only have 2 qubit, right? So H2 apply to 3. That is what I want to know. So yeah, I just copied the equation, but I decided to substitute now because it's 2 is 2 divided by 2 because n is 2, right? Summation x equal to 0, 2 to the power 2 minus 1, negative 1 to the power x dot 3. I just write dot 3. I need to be very careful. I know I'm not doing decimal multiplication, right? Because I'm doing the vector product modulus 2, right? Or whatever you call it, yeah. You mean like this? In bracket? But this is a number. This is not Okay, so this one I confuse you again. It's a vector in another space, but it's not a vector in the space we're operating. I know what you mean. He's trying to say, why don't we do this? XY, right? If we are very sure what we are doing, I think, but this is not exact just inner product, but you need to define what it is. It is modulus 2. But let's say you come up with your name, Chen inner product. Let's have something like this. I think it's okay. You can do that, right? But however, if anyone reading this paper and see what you just wrote, they will get confused. They will think that. So very important, right? When I say x dot, this is a very different thing. X inner product y in this problem is not the number x inner product y. Do you see what I mean? Because this is the basis state, maybe for a quantum mechanics state. It's not the number. You see what I mean, right? Yeah. So you cannot just put that. But that is a very quick question that you think of. So as you put x dot 3, right? And then x. Is that okay? Now what do I do? Just do it one by one. Easy. Once you have the right thing. 1 over 2 to the power square root, 2 to the power 2 over 2 is just 1, right? So let me just write it out. It is negative 1 to the power 0.3, not 0 times 3, okay? 0.3, 0, plus negative 1, 1.3, 1, plus negative 1, 2.3, 2, plus negative 1, 3.3, 3. Are you okay for this expression? Now that's very important. You need to understand what's the meaning of the equation, right? And these are some of the complex equations you can see if you read paper. Now you won't get confused. So all we need to do now is just evaluate each term. What is negative 1 to the power 0.3? Based on our definition, what is 0.3? 0 times 1 exclusive or 0 times 1. Right? So now you see this is not x dot y. Any question about this? Maybe you forgot. Why? Because just of the definition. Right? We convert x and y to binary and we just times the corresponding digit and then do exclusive OR. Yes.
So even my dot product type, they don't live in the same space. They have to be vector product.
You mean the use x? Right. We don't do this because if we write this, then we will think that we are talking about the inner product of the vector in this space, right? But this is not the vector in this space. This is just a number. I can call it vector, but yeah. So, or I should not have said this is just an inner product, then you won't get confused. right? I just say counting the number of 1 when you do pairwise multiplication. Yeah, but indeed it is something similar. Modulus 2, yeah. But this is a good question and clearly make us, it help us to make it clearer about all the meaning of everything. What is this? Negative 1 to be to the power 0 because it's 0 exclusive or 0, right? So this is 1. Okay, let's do the next one. How about 1.3? What is 1.3? What is the binary representation of 1? 0, 1, because it is 2 bit, right? So it's 0 times 1 exclusive or 1 times 1. So what is this? What is 0 exclusive 1? Exclusive or 1? Basically, we're counting the whether we have odd number of 1 or even number of 1. Do we have odd or even? What is this? No, I'm talking about this term. Not about 3, it's about 1.3. How many? Yeah. How many 1 do we have? I mean, after multiplication. 1, huh? Because it is 0. This is because we're doing exclusive OR. It's applied to both sides, right? Yeah. So let me make it clear. This is 0 exclusive OR 1 equal to negative 1 to the power 1 equals to negative 1. Similarly, what is 2.3? What is 2? 1, 0. So it will be 1 times 1 exclusive or 0 times 1. Very good. So it's negative 1, 1 exclusive or 0. You're negative 1, 1, you're negative 1, right? And then the last one is 3.3. Which is equals to 1 times 1 exclusive or 1 times 1, right? So what is 1 exclusive or 1? 0, because you have even number of 1. Okay, so what is the answer? The answer is H2 applied to 3 give me 0 minus 1 minus 1. I think I have some problem. Minus 2, right? I think I make some mistake. Minus 2 plus 3. But you understand what is the meaning of plus 3, right? It means plus 1, 1. There's a problem here. This doesn't look like normalized, right? What's the other problem? Is that what you're saying? 1 by 2. 1 by 2, right? So I say something wrong again because 1 over 2 to the power 1, of course, is 1 by 2. Somehow I thought that it is 1, right? So this is 1 over 2. So this whole thing is 1 over 2. Okay? And now you normalize, right? What is the probability of each of them when I measure? 1 by 25% or 1 by 4, 1 over 2 squared, right? So everything makes sense. So I do want you to go through this, right, in the assignment again, because the most difficult part for people like us who didn't have a strong background on linear algebra is that these are very confusing. When you read it, you need to know whether it's binary and how they are operating together, when you can separate them, and when you can combine. Okay? So this clearly shows you how you do it. Okay? Any questions? Yeah. Okay. That is because he's asking, how do you get this? Again, here is this. Let me just go here. Yeah. So here is like what? X equals to 0, equals to 0, 0. Y equals to 3, equals to 1, 1. Yeah? So, it is not just for you. I am sure some people also have the same question. 1, 0, yes. So this is 1, this is 0, right? Yeah, because I put 3 at the end. Yeah. But let me still complete this because I'm sure not everyone can follow. So x, this is x1, x0. This is y1, y0, right? So x dot y equals to x1 times y1 exclusive or x0 y0. That's why you get 0 times 1 exclusive or 0 times 1. Make sense, everyone? Say again. It is like the pairwise product exclusive or pairwise. You pair them together, right? So x1 times y1 exclusive or x0 times y0. It is depends on what you mean by exclusive or. Are you going to do pairwise exclusive? So the definition is that you need to multiply each pair and then do exclusive or. And then you can try to prove if what you're saying is equivalent, but I don't think it is. Yeah. Because now you are doing exclusive or many bit, right? What is the meaning of exclusive or many bit? Are you doing about pairwise exclusive or? And then how do you combine them to one bit? Right? You just write it down, then you will see whether it's right. But this is the definition. Not definition, that's what we prove. Okay? Okay, so let's go back to this is night review, right? To see what are the other method, right, for this Hadamard Gate to what's the purpose, right? So let's continue, and I call this method 1. We use the cat method. So this one is H2 applied to 3. We are doing the same problem. Okay? So H2 applied to 3 means what? H2 applied to 1, 1, right? Make sense? Which is equals to, which it means that y equals to y1, y0 equals to 1, 1, with y1 equal to 1, y0 equal to 1, which we know already. But this is equal to h applied to 1, tensor product h applied to 1, right? If we just want to work with the cat. Is this clear? Where 1, 1 is just one tensor product 1. Right? And then now, what do you get when I apply h to 1? Negative, can you give the 0, 1 basis, what it is? 1 over square root 2, 0 minus 1. Very good. Tensor product, the second space, second qubit. Are you okay with this? And then how do you calculate it? Multiplication, right? So this is just 1 over 2. I have 0, 0. Is it plus or minus based on this? 0, 0. I mean, in front of 0, 0. Plus, right? How about 0, 1? Minus, because I have negative 1 and 0, right? How about 1, 0? Also minus, right? How about 1, 1? Plus. And this is the same as what we did here, right? Plus, minus, minus, plus. Where do I count the number of 1? You are talking about to find the coefficient? Yeah, but no, this is just a general multiplication, right? I got 0, 0 because both of them are plus. It's just a minus b times a minus b. Something like that, right? So this minus b times minus b is just plus bb, right? Just multiplication. So, okay? You already know this, right? Nothing special. But you should have this skill to do bracket for midterm. Okay, method 2, we use, what do we do? Matrix. Again, this is just a review, right? So H2 equals to H tensor product H. Do you still remember what is the matrix form for H? 1 by root 2. So someone remember 1, 1, 1, negative 1? Good. If you forgot, put in cheat sheet. Okay, how do you do tensor product with another one? Well, the first thing, just write it down, right? And then the second thing, how do you do tensor product? For scalar, I just combine them 1/2, right? And then, what do? I can just, as if I just put everything inside, yeah, for each element, right? So 1 times 1, 1, 1, negative 1, 1 times 1, 1, 1, negative 1. This is just a temporary storage, right? It is meaningless here. Negative 1 times 1, 1, 1, negative 1. Are you okay with this, everyone? Right, you should be very familiar with this. And this gives me a big matrix. What is the size of the matrix? 4 by 4. Why? Does it make sense, 4 by 4? How many qubits we're dealing with now? 2. So it's 2 to the power 2, right? Which makes sense. So the one is 1, 1, 1, 1, 1, negative 1. The second one, 1, 1, 1, negative 1. Third one, 1, 1, 1, negative 1. The last one, opposite, right? Negative 1, negative 1, negative 1, 1. Right? Although I don't write it well, but you should not confuse you because you know how to do it. Okay? Now, then let's look at an example. What is 1, 1 in this 4-dimensional space in vector form? So it's not 1, 1, 1, 1. If you forgot, then let's do a tensor product. Okay? This is 1, tensor product 1. What is the matrix form of 1? 0, 1. Okay? Then we do tensor products, right? So don't make mistakes. 0 times 0, 1. Just do it slowly. You have plenty of time. 0, 0, 0, 1. Okay, so don't just jump in and say 1, 1, 1, 1. Because 1, 1, 1, 1 actually is a superposition. So now let's try to find out what is the result. So H2 apply for 3 equals to 1/2, 1, 1, 1, 1, 1, negative 1, negative 1, 1, 1, negative 1, negative 1, 1, negative 1, negative 1. Difficult to see. 0, 0, 0, 1. Looks very troublesome, but if you look at this is not a filter, or this column, this row times this column, which one will be left? The last one, right? Same for this one times this one. The last one, right? Because the rest is 0. So basically, the operation is to get the last column, right? This is equal to 1/2. Last column, 1, negative 1, negative 1. Is it correct? Think about that. This represent which basis? 0, 0. This one, 0, 1. This one, 1, 0. This one, 1, 1. And in D, 1, negative 1, negative 1, 1. 1, negative 1, negative 1, 1. Right? Everything is correct. Right? So this is cat method, and that is the Brown method. Okay? It can be 4 qubit. But I'm not going to torture you. It doesn't make sense to ask you to do 16 by 16 matrix, right? There must be some math that you can simplify. What's the size of 4 qubit matrix? 4, right? To the power 4, right? So 16 by 16. I'm not going to check each element to grade, right? It takes lots of time. So I'm done for today, but you can leave now if you want. I do want to, for those who are interested, I do want to show